In this example, we're going to evaluate the integral of dx over square root of 4 plus x squared. Now, this integral is the perfect candidate for trigonometric substitution, and the reasons for that are that neither regular substitution rule nor integration by parts would help us to evaluate this integral. And second, it has expression in the denominator, which is square root of 4 plus x squared, but I guess specifically 4 plus x squared. That's the right kind of expression that we want to have for trigonometric substitution. If you remember, when we do trigonometric substitution, we need to think what kind of identity, trigonometric identity, that expression resembles. Let me make a list of identities that we need to choose from. So we have three identities. Actually, two of them are the same identity, but I guess written in two different versions. Okay, the first one is 1 minus sine squared of theta equals cosine squared of theta. Then we have 1 plus tangent squared of theta equals secant squared of theta. And the third one it's the same as the second, but just rewritten in different order. Secant squared of theta minus 1 equals tangent squared of theta. Now, I'm also going to remind you that the whole purpose of trigonometric substitution is to replace expression inside the square root with some trigonometric identity of this kind, so that we can replace the left-hand side of the identity in the next, like in the following step, with the right-hand side of the identity, which is just one function raised to the second power. And that one function raised to the second power, or I should say that second power, can cancel the square root that we have here, and that will make, overall our integral simpler. Now, as we think about which of those three identities, specifically the left-hand sides, which one matches our expression the best? Well, we can see that we have 4 here, right? Number 4, constant 4, but none of the identities have 4. We have to think about that in a few seconds, but if we ignore that for now, well, then probably one that's with the plus sign, right? So we have plus here, we have plus here. The other two, they have minuses. So yeah, we're not going to use those. So somehow we want to rewrite this as 1 plus tangent squared. But how about this 4? We need 1. We don't want 4. Well, think this way. If I have 4 over here, and if I had 4 as the coefficient of the second term, what I could have done is that I could have take that 4 as the common factor and factor it out, right? If it was 4 plus 4 times something, then 4 could have been factored out. And then I would be left with 1 plus something, correct? So now, as I think about substitution, which means that what x is going to be equal to, I have to keep that in mind. Now, we already said how it will be connected to 1 plus tangent squared of theta identity because of that plus. Well, that means that x has to be, well, something involving tangent, right? So tangent of theta. Now, if I just leave it like that, then I'll have 4 plus tangent squared of theta. And again, 4 would be the problem since I want 1. But what do I need to do here so that I end up with coefficient 4 as I perform substitution? Well, if I let x be equal not just tangent but 2 tangent of theta, so if x is 2 tangent theta, then once I square that, well, because x is squared, then 2 becomes 4 and tangent becomes tangent squared. And in the following step, I would be able to factor out 4 and end up with just exactly the left-hand side of this identity. Let's try that. I'm gonna, for now, just focus on the denominator. So that's my integral. In the integral, in the denominator here, I have square root of 4 plus, now I'm not going to be skipping any steps here, so I'll take time to write all steps. X I'm replacing with 2 tangent theta. And now since x is squared, this expression 2 tangent squared is going to be squared. But I need to remember that when I square a product, each factor has to be squared. So 2 has to be squared and tangent has to be squared. So that means that I'm leaving the numerator blank, as you noticed, but I'll go back and write, the appropriate expression here in a second. So now the denominator is 4 plus 4 tangent squared of theta, right? Here it is. That's what I was trying to get. I have 4 here. That's a common factor. I can factor it out, and as soon as I factor out, and it's all going to be happening inside the square root, I will be left with 4 times 1 plus tangent squared. I'm going to write this down, but let me go back to the numerator so that I don't forget to work on that as well. Now, the numerator, the original denominator is dx. So what do I replace dx with? To find what to replace dx with, I just have to find differential dx from here, right? If x is 2 tangent theta, then dx is derivative of tangent, or derivative of 2 tangent theta. Constant stays, and then derivative of tangent is secant squared of theta, d theta, right? So that's what dx is, which means that in my original integral, dx will be replaced with 2 secant squared theta d theta. And now as I check all that, I can see that all x's are gone and everything is in terms of theta. So I'll put that numerator here. 2 secant squared theta d theta. It's still here. 2 secant squared theta d theta. I could have put constant in the front, but I have a feeling that I will be able to cancel it. So let's continue. Now, for now, I'll just leave the numerator as it is. 2 secant squared theta d theta. And now the denominator. Inside that square root, we can factor out 4. But keep in mind, that's all happening inside the square root. So square root is still here. I'm factoring out 4, so it's 4 times 1 plus tangent squared of theta. Okay, here's my identity. That's the one I was working towards, right? I wanted to obtain this left-hand side so that I can, in the next step, change it with the right-hand side, just a single function. And now that's the time to do that, right? So 1 plus tangent squared of theta, that's secant squared of theta. Let's write that. 2 secant squared of theta d theta over, I'm not skipping any steps, as you can see. If you feel comfortable, you can totally skip some of them. Okay, so everything is still happening inside square root, but now that's going to be the time to get rid of that square root. Now in this case, since I have a product inside the square root, I can apply square root to 4 and I can apply square root to secant squared. That will give me, so I'm copying down the numerator. That will give me square root of 4, that's 2, and then square root of secant squared is just secant. So next is just the basic simplification. I can divide out 2. I can divide out secant, right? Secant from the denominator is gone, and then I'll just cross out that second power. So I have just secant theta left. So that all simplifies to just simply secant theta d theta, right? And generally we just performed the second step. So the first step of this whole process was to introduce the appropriate substitution, such that a function that I choose comes from an identity that resembles that expression, and you also have to make sure that you can somehow get rid of that constant that's not 1. We did it by factoring, right? So once you perform substitution and everything is in terms of theta and trigonometric functions, then the next step is to simplify as much as you can. And then once you simplified, you look at the resulting integral and think how to evaluate it. So we got lucky in this example, and this is just a basic integration, right? You can find integral of secant theta in the table of integrals. So integral of secant theta d theta is ln of absolute value of secant theta plus tangent theta plus c. I'll say C table of integrals. You can get that result from there. Now, are we done? No. Once you integrate it at this point, so that's step 3, the last step will be to return to the variable, to the original variable of integration, which is x in our example. So I have to switch all thetas to x's. And to do that, we have to recall the original substitution. So right here, we said that x is 2 tangent theta. So to return to the original variable of integration, which is x, that's what I'll do. I will represent tangent theta in terms of x. So from this equality, tangent theta is x over 2. Now, if I know that tangent of theta is x over 2, then by constructing a right triangle, I can find all other functions of theta that I need to find. Well, I can find all of them, but I don't need all of them. I only need, let's go back to our answer. I only need to know what secant of theta is, and, oh, actually tangent of theta. I already have it, right? So that we know is x over 2. So we only need to find secant of theta, in other words, in this case. So how do we find it? So by constructing this triangle, right triangle, where I denote right angle, and then I also denoted angle theta, I need to recall that tangent of theta, or tangent of an angle in the right triangle, is defined as the opposite side to adjacent side, right? That means that if theta is here, then its opposite side has to be x, and its adjacent side has to be 2. But what is secant? Remember, we're trying to find secant. Secant theta is, well, the definition of secant, now, secant is reciprocal of cosine. Cosine is adjacent side to hypotenuse, and secant is reciprocal of that, so that's hypotenuse to adjacent side. So to find what secant of theta is in terms of x, I need to figure out what hypotenuse of that right triangle is and put that over adjacent side, which is 2, right? So I know it's going to be over something over 2. Well, that something is hypotenuse. How do we find hypotenuse? Well, we know that leg squared plus leg squared is hypotenuse squared. So hypotenuse itself is the square root of leg squared plus leg squared. Right, so leg squared plus leg squared is hypotenuse squared in the right triangle. So that's x squared plus another leg squared plus 4 equals hypotenuse squared. But if I squared both sides here to find hypotenuse, expression that I will end up with is square root of x squared plus 4. Right? So that's the hypotenuse. It means that now I can finish secant. Secant theta is square root of, you know what, it's x squared plus 4, but it's same as 4 plus x squared. I'm just trying to be consistent as to how our integral was given. Notice how we had that same square root in the denominator there, so that's not a coincidence. I will just switch the order here so it matches my original integral a little bit better, but there's no difference, right, in which order you write it. It's not a mistake to keep the original order. Okay, so long story short, we just found secant of theta, and that allows, in terms of x, right, and that allows us to rewrite our answer in terms of the original variable. So the answer will be ln of absolute value secant theta. Here it is, square root of 4 plus x squared over 2 plus tangent of theta, well, tangent of theta we had, it's x over 2, plus x over 2, and then plus c. And of course, it's okay to leave it like that, or you can combine, since those two fractions have same denominator anyway, right? Why not to combine them together? So absolute value of the numerator is square root of 4 plus x squared, and then plus x, denominator is 2, plus c. So that's going to be the answer.